In this video, I'm trying to use a GPS as a variable frequency reference standard to check the accuracy of anything in the lab that measures and displays frequencies. I'm going to briefly cover the type of GPS that can be used and the ways to construct such a standard and how I made mine. When I started to use my new frequency reference, I found that the output signal is often full of jitter. A good part of this video is therefore about my investigation into the causes of the jitter and workarounds to avoid it. The basic idea behind using a GPS as a frequency standard is that many provide a special output signal called pulse per second or PPS. This output is usually a 1 Hz signal which, depending on the model, has its rising or falling slope synchronized to occur precisely at the moment the GPS time advances to the next second. Of course, this only works while the GPS sees enough satellites to work out its position and the GPS time. The traditional way of using a GPS as a frequency standard is to let it correct a separate oscillator as shown in this very simplified diagram. In this example, an already highly stable oscillator circuit outputs a 10 MHz signal. This output is tapped and divided down to 1 Hz and continuously compared with the accurate 1 Hz from the PPS signal. I try to show the two signals here on the right. Any drift of the local oscillator, like I show here grossly out of proportion, leads to a tuning correction signal to the oscillator, which will therefore stay locked to the PPS. This produces an accurate reference with a high quality output signal. The drawback is the amount of components needed and that it produces just one fixed frequency. Although with a little extra effort you can tap some of the stages in the already present divider to give you a few additional fixed frequency outputs such as 1 MHz, 100 kHz and so on. GPS receivers that allow the PPS signal to be changed open the possibility of an intriguing simplification. For example, instead of fitting exactly one pulse into the 1 second GPS window, it may be told to fit 10 million. For this to work, you need a controller of sorts that can send a message in the right format to the GPS to change the PPS frequency to something else. Another component needed is an output stage to amplify the PPS signal to make it suitable for general use. A key advantage of this concept is that it allows the controller to send any target frequency you wish to the GPS, so nothing stops you from asking it to produce a reference frequency of 242 kHz, for example. This is a simplified diagram of such a GPS frequency standard designed by Louis Cully on his highly recommended YouTube channel. It is a self-contained unit with a controller part handled by an Arduino Nano, allowing arbitrary frequency selection through a keypad and a 2-line LCD display. The GPS is connected through a serial interface and the design includes an output stage for the PPS signal. It's a very tempting and neat design, and the only reason why I did not build it was that I really don't need a frequency standard often enough to justify the effort and costs to put this together in a decent enclosure on a permanent basis. For my own purposes, I'm quite happy with the minimalistic design shown here. I use a PC as a controller, connect the GPS via USB, which also provides power, and connect an output stage for the PPS signal. All this put together with flying connections only if and when I need it, which allows me to use the GPS for other things when I don't need reference frequencies. What type of GPS do we need for this? Firstly, it needs to have a PPS output that can be accessed easily. Secondly, of course, it needs to allow changing the PPS frequency through a message of some kind and either come with existing software that allows us to do this or with a documentation that allows us to write our own software. Thirdly, it should have a USB interface because this will make powering the unit and the connection to the PC so much more convenient. I selected the u-blox Neo 7N GPS module. Here's an extract of the datasheet. On the selection of product features, note that it includes USB as an interface. The 7N also has programmable flash memory, which would allow changing the default PPS after power up from 1 Hz to say 1 MHz. If you just need that frequency, you would then not even need a PC anymore and could use a USB power bank to make it portable too. The 7N also has an internal temperature control crystal oscillator, which not only speeds up the synchronization with the satellites, but can produce reasonable stable PPS frequencies without satellite reception. On the other page, note that a 7N allows the selection of the time pulse signal frequency up to 10 MHz. On the accuracy of the PPS, the root mean square is 30 nanoseconds, and in 99% of the cases it's at least 60 nanoseconds. At 10 MHz, one period is 100 nanoseconds long, and at 50% duty cycle, a pulse is 50 nanoseconds wide. We may be missing or getting one extra pulse in 10 million, which is pretty good. On the u-blox website, you can download the documentation for the message definition as well as a free tool called uCenter, which allows you to communicate with the u-blox GPS. As you see, uCenter is only available as a Windows application and needs at least Vista or better. I use Linux on my PC, and fortunately uCenter works fine if you use Wine emulating Windows 10. There are also Windows device drivers available for download on the u-blox website, but as uCenter in Linux works without those drivers, I can't tell you anything about them. With the Neo 7N ticking all the boxes, it's time to get hands-on. This is a close-up of a GPS board I got from eBay for about £12. There are many similar ones available. Here's the u-blox Neo 7N chip, which takes most of the space on this side of the PCB. Underneath this cover are not only the actual receiver, but a number of other components, in particular the flash memory, the temperature control crystal oscillator, and a real-time clock. The remaining components on the PCB are an LED connected to the PPS signal, a 5-pin header, a micro USB connector for power and serial data, a voltage regulator to get the 5 volts from the USB down to 3.3 volts for the Neo 7N module, and a rechargeable battery for the real-time clock. On the other side of the PCB, we see the labels explaining the signals on the 5-pin header: VCC and ground, serial transmit and receive, and the PPS. The remaining part is almost completely covered by the onboard antenna and an SMA-style connector with power provisioning for the active external antenna. That big onboard antenna notwithstanding, I found that using a GPS indoor means you're almost guaranteed to need an external antenna. These can be bought quite cheaply on the internet. I think I paid less than £5 for mine. I decided to copy the output stage Louis Cully used in his Arduino controlled GPS frequency reference standard mentioned earlier. Here are the schematics for his design. The output stage is in this highlighted area. On the left is the output stage again, this time with all other components removed. It uses 6 Schmitt-Trigger inverters integrated into one chip 74AC14. On the lower right, you see parts of the datasheet with the pinouts and the function table. Schmitt-Triggers have 2 different thresholds, shown in this diagram on the output in blue of a Schmitt-Trigger inverter when receiving the triangular input shown in red. The output stays high until the input exceeds the higher threshold, then flips and remains low until the input falls below the lower threshold. Because of the 2 different thresholds, Schmitt-Triggers are far better than simple one-threshold comparators when suppressing noise in a signal. Back to the output stage schematics and how it works. The input of the first gate is preset with 2 10K resistors to half of VCC. The PPS signal is AC coupled into this preset gate using a 10F capacitor. The output of that first gate is then split and each path run through a second inverter. One of these paths forms a TTL compatible output labeled option in Lewis's diagram. The other goes into 3 further inverters with their outputs summed together through 150 ohm resistors to form a high power 50 ohm output. A 100 NF capacitor across the power rail is used to decouple the chip's power supply. I looked into my parts bin and found a small piece of leftover perf board that's just the right size. To conveniently connect to the GPS board, I scavenged this audio motherboard connector from an old PC. It has one usable row of 5 pins, and trimming the cables that I don't need, it ended up like this, with a slightly non-conventional color coding, namely brown for VCC, red for ground and blue for PPS. The other items are the chip, resistors and capacitors needed for the output circuit. For small projects, I usually do the design in Libreoffice Draw because it allows me to work in a convenient scale and supports layers that can be made visible or not and write protected. Here you see 3 views of the output stage with different numbers of layers turned on. The first on the left is just the perf board, the holes represented by the blue discs. The second in the middle is the view of the component side, with the outline of the ICs, resistors, capacitors, a few wire links, and the output terminals. In the IC outline, I added which pins are used by the inverter inputs and outputs because that makes checking the wiring for correctness easier. The third view on the right shows the solder side as you would see it when doing the actual soldering. The orange discs represents actual solder parts and the orange lines represent wire links on the solder side. The correctness of the wiring is easy to check. The PPS signal goes via the 10 NF capacitor to the input of the first inverter. The output of this inverter goes to the input of the second as well as via this link to the third in the row which provides the TTL output option. The output of the second inverter goes across to the other side of the chip and through the 2 wire links into the inputs of all 3 inverters on that side. Each of their outputs goes through 150 ohm resistors to the output pin. VCC goes through this link to one leg of the 100 NF decoupling capacitor, one 10K resistor, and then to the chip. Ground goes to the other leg of the 100 NF capacitor, the other 10K resistor, then to the chip, and then to the ground output pin. This is the finished output board. Not terribly pretty, but functional. I did many of the short and straight connections on the solder side using folded down component leads instead of separate wires. This makes for quick progress as long as you're aware that you're never going to be able to desolder any of these later. This is UCenter running and talking to the GPS board. It is well worth exploring the many features, but for now I only want to change the PPS frequency. To do that, you open View, Message View. Here you see the many different messages that can be exchanged. The first part are the well-known NMEA 183 messages, all starting with G. Further down we find the proprietary UBX messages, and the one we need is called TP5 and part of CFG. This is the default setting, which generates the 1 Hz PPS signal. This window with its many options seems confusing, but we only need a few settings. First, we want to specify frequency and duty cycle and not period and length. Also, we want to make sure that these 5 tick boxes are all set and that 0 time pulse is selected. The final preparation is to set the duty cycle to 50% in both of these fields. They are now just the two frequency input fields of interest. The top is only used when there are not enough satellites, and the lower one is only used when there are enough. So, assuming the GPS receives properly, all your changes should only be in the lower field. If the GPS loses log, that is the number of satellites is too low, the PPS switch to whatever you input in the upper field and ignore the lower one. If you have confidence that the local oscillator in the GPS isn't drifting too far off during periods of no reception, you can use the upper field and still generate frequencies. Or you can just set it to 4 Hz and leave it at that, so when you suddenly notice the PPS LED blinking frantically, you know you've just lost satellite reception. Once you type a frequency, for example 1000 Hz, just press send to send it to the board. Just edit the value and repeat for other frequencies, for example 10 MHz. Note that all your changes are only in the GPS RAM and will be lost at reset or power loss. On the 7N chip, you can use uCenter to save the changes into flash, which means the GPS will use your chosen frequency automatically after power up. This is the 10 MHz signal we just specified in uCenter. I'm using the 50 ohm output signal, and I terminated the scope with a 50 ohm resistor to reduce ringing at least somewhat on the higher frequencies. That's why the signal is showing only just over 2 volts amplitude. While this output looks terrible and full of jitter, other frequencies were clean enough. Let me run you through a couple of examples. As the scope counter is limited, I hooked up another frequency counter as well. This is the summary of the test you just saw, which by the way is fully reproducible. You can run this again and again with the same results. 16 different frequencies, of which 10 are clean and 6 have jitter. I included a 12 MHz case just to show that it isn't the high frequencies above 8 MHz or so that cause the problems. A matching pattern occurs if we assume that all frequencies are derived by dividing a frequency of 24 MHz. All frequencies with a divisor that isn't a whole number have jitter, while those with a whole number appear safe. The 24 MHz, incidentally, is not mentioned anywhere in the documentation. I only picked it because it fits the measurements perfectly. So how many jitter-safe frequencies are there? This is actually not so straightforward to answer. obviously there are 24 million different whole number devices that you could use to create a new frequency out of 24 megahertz, but the overwhelming majority are totally useless. Here's an example. Divide 24 megahertz by 3 and you get 8. Divide by 4 to get 6, and so on. Divide by 24 million to get 1 hertz. But so do almost 12 million other devices in the range from 12 million and 1 to 24 million. All you get is 1 hertz with different digits behind the decimal point, but unfortunately the GPS only accepts whole number frequencies in the message to change PPS, which leads to 12 million cases of just 1 hertz. The same is true for most of the higher devices. The next 4 million devices give you 4 million versions of 2 hertz. Just the two frequencies of 1 hertz and 2 hertz have already used up 16 million out of 24 million possible devices. So printing a book of safe frequencies based on counting up devices from 1 to 24 million would be a long, boring and pretty useless waste of paper. Half of all pages containing just the value 1 hertz and another quarter of pages just the value 2 hertz, and so on. I found the easiest way to determine the safe frequencies, especially for higher devices producing lots of duplicates, was to write a little program that goes brute force through each of the 24 million possible devices, but only prints those that cause a change in the integer part of the frequency. This is my safe frequency list between 1 hertz and 8 megahertz. It contains 9,795 entries. Notice that it stops at 8 megahertz. The next higher safe frequency would be 12 megahertz, but although it works, that's beyond the 10 megahertz maximum for PPS given in the datasheet. When scrolling through the list, did you notice the skewed distribution? It takes seemingly forever to get from 1 hertz to 10 kilohertz, but then it gets much faster to reach the megahertz range. This rough chart shows how the safe frequencies are distributed. The lower the frequency, the more devices exist, and higher frequencies have very few devices. This is of course no surprise, as dividing by 2 already halves the frequency and dividing by 3 thirds it, while there's not much difference when dividing by say 500 and 501. This is the underlying reason for the little statistic down here, which shows how many of the 9,794 frequencies are in each of the commonly used range brackets. In the first 3 ranges, from 1 to 9, from 100 to 99, and from 100 to 999 Hz, all frequencies are safe. In the next range, from 1 kHz to 9.999 kHz, still a respectable 71% of all frequencies are safe. Not so great in the 10K to 100K range, which contains just 2,160 safe frequencies, or 2.4%. But at the higher ranges, the picture is very bleak, and don't forget, each higher range is 10 times the size of the previous one. At the top end, we just have 22 safe frequencies for 10 million possible ones. In fact, if you think of the practical use of safe frequencies, the picture is actually worse. If you recall, I mentioned that the list suppresses the fraction part of frequencies because the message to the GPS only allows whole numbers. For example, the list contains values such as 3.428571 MHz or 2.666666 MHz. But if we actually do the calculation, it turns out that the real magic frequencies are these highlighted numbers, which you can't enter into uCenter. In fact, of the 9,794 safe frequencies on the list, only 138 are whole numbers. Since you can't enter the exact number required, it is therefore worthwhile to test the behavior of the chip when you request a few of those almost safe frequencies by typing in the closest integer instead. As you can see, all 16 turned out to be jitter-free. The first 8 on the left are in fact the highest almost safe frequencies. I examined those first because for reasons we shall see, higher frequencies are more prone to noticeable jitter. I picked the 8 almost safe frequencies on the right randomly from the lower frequencies in the safe frequency list. What about when you need a frequency that isn't on the safe frequency list? Let's find out. Here's the summary of frequencies I tried. I looked for useful frequencies that have an application in the real world and give a reasonable coverage over the whole range of 10 MHz. When I couldn't find one, I picked an arbitrary one. What all these frequencies have in common is that they are not on the list of safe frequencies because they need a divisor that isn't the whole number. You can see the divisors rounded to 2 decimals here. It is obvious that any frequency above 120 kHz or so that is not on the safe frequency will be affected by noticeable jitter, which gets worse the higher the frequency. Why is this happening? There isn't anything in the datasheet that I could find. However, the problem is obviously confined to frequencies needing divisors that are not whole numbers. This led me to investigate what solutions hardware designers use to create a programmable divider that can handle divisors that are not whole numbers. The basic idea works like this. We want, for example, 10 MHz out of 24 MHz, which needs a divisor of 2.4, which we can't do because we can't do fractions. So what we do is the next best thing and get the 2 closest frequencies instead by dividing by 2 and 3. Both are whole numbers and therefore okay. These 2 divisors are normally called n and n plus 1. The frequency using the n divisor is obviously higher than the one we want. It's 12 MHz instead of 10. And of course the frequency using the n plus 1 divider is too low. It's 8 MHz instead of 10. A programmable divider can now employ some logic to quickly switch between the too low and too high frequencies in such a way that the average frequency at the output becomes the desired target frequency. The dual modulus divider is probably the simplest way to make such a divider. This gray box here represents the dual modulus divider, and I only show it 3 times to explain its status at different stages. On the top here we have our base frequency of 24 MHz and the desired target frequency of 10 MHz, which requires a divisor of 2.4. The whole part of the divisor is used to load the n and n plus 1 values, which in this case are 2 and 3. The target frequency, in this case 10 million, is loaded into a counter called the n counter, and a second counter called the n plus 1 counter is loaded with the integer part of the result of multiplying the fraction part, that is 0.4, with the target frequency of 10 million, and that produces in this case 4 million. Because the n+1 counter is not 0, the divider uses the first modulus, that is the n+1 value, to divide the base frequency and get 8 MHz, which means one period is 125 nanoseconds long, 62.5 nanoseconds high and 62.5 nanoseconds low. In the first phase of the divider, it now uses this 8 MHz signal to decrement both counters and for the output. Phase 2 is reached when the n+1 counter reaches 0. This means we have now just sent 4 million cycles of 125 nanoseconds length, which took 0.5 seconds. The n counter is now 4 million lower and at 6 million. The divider now switches to the second frequency, which is n, and gets 12 MHz, which means one period is now 83.3 nanoseconds long, 42 nanoseconds high and 42 nanoseconds low. It uses this 12 MHz signal to decrement the counter n and for the output. Eventually the n counter reaches 0 as well. This means we have now added a further 6 million cycles of 83.3 nanoseconds length to the output, which took another 0.5 seconds. Overall, in 1 second, we have therefore sent 4 million plus 6 million, that's 10 million pulses or 10 megahertz to the output. Next, the counters are reloaded with the original values and the process repeats. So the 10 megahertz frequency, which is one of those not on the safe list, is essentially constructed out of bits of 12 megahertz and 8 megahertz, which is why it has so much jitter. Let's see how the dual modulus divider handles a safe frequency for comparison. This is what happens if you enter a safe target frequency of 4 MHz, which also has a whole number divider, in this case 6. The process is exactly as before, n and n+1 frequencies selected and n+1 counters loaded, except because there isn't a fraction part, the n+1 counter is already 0. This means phase 1 or the output of the n+1 frequency never happens, because a 0 n+1 counter causes the divider to move immediately to phase 2. Phase 2, as before, uses the n frequency to decrement the n counter and for the output. When reaching 0, it goes back to phase 1 to repeat the cycle. As the n frequency is exactly the right frequency we want and no other frequency is needed to produce it, the output is pure and contains no jitter. Let's try one of the almost safe frequencies from the safe frequency list. This is what a dual modulus divider would do if we enter one of the frequencies that is almost safe. Remember, in this case what we really wanted is the frequency that corresponds to a divisor of 7, but as we can only enter whole number frequencies, we end up with this slightly crazy divisor. The divider is loaded as before using 7 and 8 as n and n+1 frequencies, and the n+1 counter ends up to contain just a value of 3, which is almost but not quite 0. In phase 1, the divider therefore switches to the first modulus and uses the n+1 frequency of 3 MHz to decrement both counters and for the output. After just 3 cycles, the n+1 counter reaches 0, and in phase 2, the divider uses the second modulus and 3.428 MHz for another 3.4 million cycles. The output is therefore not 100% pure frequency as for a true safe frequency, but it contains just a tiny number of cycles of a different frequency. In this case, the ratio is about 1 in a million. So yes, these almost safe frequencies are technically not completely jitter-free, but for all practical purposes probably good enough. If we go briefly back to the very unsafe case of 10 MHz, the dual modulus divider suggests that the output contains basically pulse trains of half a second of 8 MHz followed by half a second of 12 MHz. Let's have a closer look and see if that's the case. This is the 10 MHz signal. If we just do a single acquisition, we can see that the pulse width changes between two distinct values almost with every other pulse. Now, for example, we can see a short pulse is followed by two long ones and then by at least three short ones. I'm trying to measure the pulse width using the vertical cursors, which I'm not using very often, hence the somewhat clunky operation. The interesting part is the bx minus ax value, which is about 14 nanoseconds, 39 nanoseconds, which is coming from a 12 MHz frequency. Now for the wider pulse, about 61 nanoseconds, which comes from a 8 MHz signal. Another about 64 nanoseconds. And see the short one. Back to 42 nanoseconds, which corresponds to 12 MHz again. I used this snapshot of the scope to mark the length of each pulse and gap. The two values are 62.5 nanoseconds in light blue and 41.6 nanoseconds in magenta. These correspond to 8 MHz and 12 MHz as shown here. It is very clear that the GPS does not simply produce a sequence of some n+1 frequency cycles followed by some more with n frequency as suggested by the simple dual modulus divider. Instead, the divider used by the GPS obviously not only intermingles the two frequencies far more, it even breaks individual periods, for example using a pulse width of 62.5 nanoseconds followed by a gap of 41.6 here, or the reverse here. There are dividers that can do that, for example the delta sigma fractional n synthesizer, but these are of course a lot more complex than dual modulus. Moreover, since all these dividers do is essentially a more thorough mixing of the n and n+1 frequencies while maintaining their average ratio, the basic observation on jitter based on the dual modulus principle is still valid. So where do we stand? For all practical purposes, I think even if you miss a safe frequency, the jitter for frequencies below 100 to 120 kHz is very small and can be pretty much ignored. Depending on how jitter sensitive your application is, you may want to be careful with frequencies higher than that and stick to jitter safe frequencies. These are the frequencies with divisors from 3 to 200, which you see here. I'm thinking to add a safe frequency only option into the little utility I wrote to replace uCenter, but I'll cover that in a follow-on video. Because of the way the output signal is assembled from bits of different frequencies, I would not use this method as a frequency generator for producing high-quality signals for general use at arbitrary frequencies. If you need that, you better look for a decent function generator instead. On the much smaller scale of using it only as a frequency standard for checking digital frequency counters and the like, I think it's actually very usable. The signal may, at times, not be very clean, but it's always of the correct frequency. That is, you get a specified number of pulses in a highly accurate 1-second window, and you can avoid the worst of a jitter if you choose the right output frequency. Thank you for watching.